All right. Welcome again to this second iteration of the Bridge program on planning reasoning in natural language with foundation models. My name is Shirin Sohrabi. I'm from IBM, and I'm going to give a very brief introduction to AI planning. And feel free to interrupt me during this talk. So if you have any questions, just raise your hand. I'll be happy to answer them as we go through this session. All right, so here's an outline of this tutorial. I'm going to sort of separate it into two sections. First is the introduction. So what is AI planning? And in that, I'm going to briefly cover three parts. What kind of planning problems do we have? Also known as planning formalisms. What kind of solutions am I looking for? Also known as computational problems. And how can I describe my planning problem, also known as planning languages? The second part will cover the solving of the planning problems, and I'm going to separate them into three sections: pre, early, and modern LLM era. All right, so let's get started with the intro. So what is AI planning? So AI planning is a long-standing subfield of artificial intelligence. It dates back to 1960s, and planning can be viewed as a form of general problem solving. It focuses on automating the sequential decision-making processes. So in a simplest form, looking at this example, you have some sort of a starting state, you have a goal state, you have your actions described in some declarative way, and the objective here is to synthesize a plan that will take you from the initial state to a goal that will be guaranteed to achieve the goal objectives. Example to ground this terminology would be in the transportation or logistic domains, where your initial state will have some objects, and these are, for example, packages, cars, trucks, the initial location of all of these transportation modes. And the goal would be to deliver these packages to some desired destination. So then the plan would be, how do you go from your initial state following the applicable actions so that the goal state will be achieved or guaranteed to be achieved. In many realistic domains, the space of possible plans is large, so it's very important to have an efficient way to solve it and optimize. And also note that in some cases, you may need more than just one plan. So in some cases, it's enough to just compute one plan, and in some cases, you want to have a set of alternative plans that you can choose and evaluate from. All right, so AI planning sits well with autonomous systems. So in autonomous systems, when you have to, you have an objective, you have to, plan for it ahead of time. Example of that would be, let's say, in robotics, example in NASA, where you have a mission in space and you have a long duration of, this mission that you want to make sure you have a valid and reliable plan for. There are many other examples of AI planning, including robotics, transportation, cybersecurity, dialogue, or scheduling cranes in some industrial settings. So let's go a little bit on a mathematical formalism of what a planning problem would be. So in mathematical terms, a planning problem would be described as following. You have a finite and discrete state space S. You have a known initial state S0. You have a set of states that would be designated as goal states. You have a set of applicable actions. You have deterministic transition function that will take you from a given state and an action to the next state. You may also have a non-negative action cost associated with each action that you have. So then a solution would be a sequence of applicable actions that maps this initial state as 0 into a goal state. And the plan or the solution would be called optimal if it minimizes the sum of the action costs. So in all but toy examples, this system could actually be quite large. So it's very difficult, or in some cases is impossible to even represent them in explicit format. So instead, one way to represent this system is to use this black box representation. So all you need for the black box representation is two implementation of two functions. One is a goal test, which is basically a Boolean, true or false, if the state is a goal state. And the second is successor state functions that will take you from a state to the next state. So that would be all that you need to represent this planning problem. However, you can think about the, what the solution will look like here. The solution would be basically applying from the initial state a set of successors in order, applicable successors, to achieve the goal. But this solution essentially maps to a path in the transition graph. And what makes the planning problem really difficult or hard is that the state space could be quite large. So one way that in the planning community people looked at it is to define and propose different planning languages. I'm going to cover one today that basically represents these large state space in a compact way. So in the planning language, you describe the objects, the initial state, the goal, the types that you have, the predicates, and the actions with precondition and effects. And what you actually get is that you can, once you define the planning language, the black box representation could be driven automatically from the planning language. And these days, people write things in natural language, right? So here's an example of a natural language planning problem. This is called a game of 24. It's a mathematical card game in which the objective is to find a way to manipulate 4 integers so that the end result is 24. So you have 4 numbers. You have to do mathematical operations on these 4 numbers. You can only use any number once, and the end will have to be a number 24. So what is now an interesting challenge, an interesting problem, is how to go from this natural language representation of a planning problem to a compact planning language. And furthermore, how do we possibly go from the natural language representation into just a black box representation of a planning problem? Any questions so far? All right, so what is important to note is that the planning problem or planning formalism is not just one planning problem, but in a most simplest case, we have what's called a classical planning problem. And in a classical planning problem, a number of different assumptions are made to make things a little bit more simple. And everything that you see here sort of written in blue are the assumptions that are made in a classical planning problem. For example, the initial state is known. The action dynamic is deterministic, instantaneous. We have discrete and finite state space. You have no hierarchies. You only have goals, and these are hard goals. Now, if you relax some or one of these assumptions, then you will get many different planning formalisms. And some of them I'm highlighting here. Everything you see in red are the assumptions that are relaxed when you go beyond a simple classical planning problem. So for example, in a numeric planning, you have numeric state variables, you have infinite state spaces. In net benefit or oversubscription planning, you have utilities, you have potentially no hard goals. You possibly have no hard goals, but you may have some other preferences that you have to deal with. In conformal planning, your initial state is not known, and so on and so forth. So this planning problem is not just one, it's a whole family of planning formalisms. Now, given a planning formalism, then the question would be, what is the computational problem that you're trying to solve? Really depends on what you're trying to to address. In a classical or numeric planning formalism, these are the following computational problems. In some cases, you just want to find one plan, and quicker, that's better, and that's called agile planning. If you want to find a plan, cheaper the better, but you don't really care about finding the cheapest, then you are in what's called a satisficing planning. If you want to find a plan, but you want to make sure it's the cheapest of all, that would be called cost optimal planning. And if you want to find more than just one plan, and there are a family of different computational problems that deal with that, some that find a set of plans, all of them of low quality, that would be called top K, or top quality, or a set of diverse plans with different metric criteria for that. Now, if you go beyond classical planning, then there are a number of other computational problems that I'm highlighting here. All right, so as I said before, one of the ways to represent a planning knowledge is to use a planning language. One of the most popular planning languages in the planning literature is called PDDL, or Planning Domain Description Language. There are other planning representations like STRIPS or ADL that I will not cover today. So in PDDL, you define two things. You define the domain. That's defined, in this example would be in the center. And you also define a problem. And the problem would be what's on the left side. In a domain, you describe all the possible actions that you have access to, as well as the different predicates that you have. In a problem, you define your initial state and your goal state. So let's look at this example a little bit more detail. This is elevator domain, or what's called a myconic domain. So in this domain, you have a set of predicates that's highlighted in the center. For example, you have origin of different, you have different floors, and people are in different floors originally, and they need to move to a different floor as their destination. You have a set of passengers, you have an elevator, you know where the original location of that elevator is, and you have access to these four actions. The four actions are boarding a passenger to an elevator, departing a passenger from an elevator, and the actual movement of an elevator. Elevator goes up or down. In your problem statement on the left, you define what are the different passengers. Here we have passenger P0 to P3. You also have the different floors, floor 0 to floor 7. You also define the relationship between the floors. Floor 1 is above floor 0. You also define the initial location of the passengers and where you want the passengers to go. Now, the goal would be to serve all the passengers, meaning that you want the passengers to go into their final destination. So here, you give these two files, the domain file and the problem file, to a planner. And the planner automatically finds a plan, and that plan is represented on the right, which is basically a sequence of actions that would take you from the initial state to a goal state. So normally, in a planning community, we have international planning competition, and these domains are driven from that competition. And normally, you have a fixed domain. So the domain for the elevator would be this one. It will not change, but the planning specification or planning instances, the problem file would change depending on how many passengers, on how many floors you have, and that basically creates a more complicated or complex problem instance for you. All right. Any questions on PDDL? All right. So we covered what different planning formalisms are, the different computational problems. We also briefly talked about one example of a compact representation of a planning problem using PDDL or planning domain the definition language. Now let's go to the second part of the tutorial, which is, okay, now how do we solve these planning problems? Let's start with the pre-LLM era. So the general framework for solving a planning problem could be sort of partitioned into three sections, or three important problems that you need to address. One is what's called a model acquisition problem, which is how do you actually get a PDDL that it would be required as an input to the planner. Sometimes the PDDL could be learned automatically, but a lot of time in the pre-LLM era, the PDDL was written manually by experts that know what the domain is about. So this is by itself, the huge topic in the planning community, this model acquisition problem. Now that you have the PDDL or you have the planning model, you give it to a planner, and this planner, this AI planner, has to figure out how to efficiently find solutions for you in this model. So a lot of focus in the planning community has been on developing planners that are efficient and reliable. Now that you run an AI planner, you get a plan, or in some cases, you get a set of plans, and then you have to post-process and actually execute these plans. So that's the execution part. So how do you efficiently execute these solutions in your environment? Now, in some cases, you have this feedback loop. You learn from the environment. In some cases, you need to change your description of the actions. The preconditions or effects may be wrong and you need to fix them. And in some cases, the cost of these actions need to be updated. So then you go back, you update your planning model and have this loop that continuously runs. But how do you really solve a classical PDDL planning problem? So you have the PDDL, you gave it to a planner, and the planner job is to find us a plan or a set of plans. So here's an example. You have, or like a visual representation of this problem. You have your initial state. You have your goal state. So essentially, you need to find a path in this graph, right? That will take you from the initial state to a goal. So a path will correspond to a plan. In planning literature, a number of different search algorithms have been developed. Some of these search algorithms are working in like local search, for example, hill climbing. You have some search algorithms that work in global search, for example, breadth first search, depth first search, and so on. And some of these heuristics are uninformed. So all you need is the goal state and successor states. Some of these heuristics are informed, for example, a star. So in a star, you can actually inform it by heuristics. So what does heuristics here mean is that you can sort of provide some estimates on how far you are from the goal. So distant estimates will be used. And if that heuristic is admissible and it's used together with a star, then you will be guaranteed to find the lowest or cheapest cost plan. Now, during the planning literature, they spend a lot of time on figuring out the efficient heuristics and efficient search algorithms. so that you don't have to explore this huge, gigantic search space. You only need to explore a fraction of the search space to find plans efficiently, and can deal with tens of thousands of actions in a plan. There are many different planners and tools available that people can use. Some of them I'm highlighting here, some of the most probably popular ones. I want to sort of also note that each planner is really could be tackling a different planning formalism and a different computational problem. So for example, let's say in top K planners, is still you're in a classical sense, but the computational problem here would be to find a set of cheap plans or lowest quality plans. And I also want to note that any planner that's developed here is reliable, is sound and complete, meaning that if there's a solution, it will find it. And we'll sort of see the contrast as we move through the LLM era. All right, so let's switch to now early LLM era. Most of the focus since 2022 was to use an LLM as a planner instead of the AI planning AI planners that are available. So here you use an LLM at inference time, and you use it to plan. So here's some citations on use of LLM as a planner. Now, these papers sort of partitioned into two groups. Some say that, in some cases, LLM is a great planner, and in some cases, there are papers that actually been titled LLMs cannot plan. Now, quickly, it was realized that you actually need search, because search is a big problem. The search space is quite huge. The data space is huge. So then there are a lot of different planners, including popular thought of search, theory of thought, paper, not thought of search, the theory of thought paper that says, okay, let's use LLM as an external search component. We are going to use a large language model at inference time to guide us through this huge search. We're going to use it in multiple different places. We can use LLM to give us some distance estimates, to tell us whether we reached a dead end, to tell us whether the value of these nodes, what are the next nodes that are available. Now, because LLMs are used at inference time, you're going to see a lot of different, it's very expensive. You're going to call the LLM many, many, many times. So to bound this number of, the LLM calls, there are many different bounds that these papers have put in place. For example, you can put a bound on the exact number of LLM calls. You can put a bound on the depth of the search. You can put a bound on the branching factor. And once you put all these bounds, you essentially lose a lot of properties that come with a standard, pre-LLM era planning or planners. So the properties that you're going to lose is soundness, completeness, and optimality. So these approaches are not sound. They're using LLM. They have bounds. If there's a solution, you may not actually find it, and is actually not optimal as well. Now, one note here is that if there is a validator, then you can potentially make some of these approaches sound. Another thing is to look at the computational complexity of all of these approaches. And in our 2024 NeurIPS paper that's cited here, we looked at some of these approaches, including, chain of thought, react, review, so on. We have the complexity, worst case complexity in the second column. And we also looked at the four popular domains. And you can see these approaches are quite, the complexity of them is large. And we looked at two things also: the fraction, the fraction of state space that these approaches look at, and that varies. In some approaches, is small, like 0.02, versus in reasoning as planning RAP, it looks at a huge number of states to find the solution. And also another thing to note is the number of calls to the LLM. You can see some of them is in the millions. So these approaches are not efficient, not reliable, and also whatever they find on one instance is not carried over to the next instance. So they have to start from scratch every time. They have to find a solution. But why did it work in the first place? So we do see a lot of papers that say, these approaches actually work. To give you some ideas, I'm going to show two examples, but there are many different examples that contradict that they actually, they didn't really work. The first example is this gripper domain. The gripper domain, look at the left side of this slide. You have a gripper with two hands, left and right. You have two rooms, room A and room B. You have objects in red that are in room A. They need to move to room B. So every plan will have this sort of sequence, pick up, move, drop, move, pick up, move, drop. And they follow that sort of pattern. Now, if you want to have a more complicated example, generally right now, the generators for this domain only increases the number of objects from room A. But there's going to be still two rooms, room A and room B, and all the objects are going to be in room A. So that's what the current numbers on evaluations of this benchmark shows. Now, if you change the instance generator to what you see on the right of this slide, so you actually increase the number of rooms. So you add a room C, or you have objects that do not just start from room A, these problems become difficult and LLM cannot solve them. Become computationally very difficult for LLM. But the current instance generators only have instances that are shown on the left. So conclusion here would be to be aware of the instance generator limitations. And you really need to show generalizations that go in outside of the training set and show performance on multiple domains before you can, claim victory on solving these planning problems. We have a position paper that's on the bottom right, where it's titled "Make Planning Research Rigorous Again," where it's available on arXiv, and we actually highlight some of these problems that we see in the literature right now. And the second example that I'm going to highlight, it comes from a blocks world domain. So in blocks world is a simple planning problem. You have a set of objects. They start from initial state. You see, the configuration of the initial state on the top left. And you want to move to a goal state. So you have a configuration that you want to achieve. How do these plans look like? You have pick up, put down, stack, and unstack. So they only have 4 actions. And whenever you pick up an object, it has to be followed by stack. When you stack, it will be followed by either unstack or pick up. And when you unstack, it has to follow to stack and put down. And finally, when you put down an object, it has to be followed by unstack and pick up. So what does it mean? Is that if you restrict the number of actions in your plan to be less than 10, at most 5 blocks will be moved. Even if the instance generator has hundreds of blocks, it doesn't matter. You still have only 5 blocks. And the total number of possible plans that you will have is just in the 1300s. So this becomes a really, really easy planning problem. Most importantly, it will potentially be in your training set, right? So when you train on these large collections, there are patterns that most likely would appear in your training set. So again, the conclusion would be there are many planning domains out there. Blocksport is just one simplest. Unfortunately, we see that as the one that many papers claim as victory. We want to show generalization that goes beyond the training set, and we want to show performance on many, many domains. And again, we highlight some of these in our position paper. All right, so let me conclude with the modern LLM era. And here I'm going to highlight 3 recent approaches. All of these 3 approaches, in contrast with what I talked about before, are reliable and much more efficient. They seem to be very promising as we move towards a use of planning in the LLM era. The first is, it's called LLM as a search component generator. So this is in contrast with what I talked about before. So what I talked about before was to use an LLM as an external search during inference time. Here, these approaches that are highlighted here would actually use LLM at solution construction time. You use an LLM to get you 2 functions: code for a goal state, goal test, and a successor state function. And that would be all you need to put these 2 functions in a sound and complete search algorithm and run for all of the instances that you have in your domain. So let me just show you some numbers. In contrast with what we saw before, the bottom row, it's called TOS approach. That's the one we proposed. You can see the complexity is O of 1. In all of these 4 domains, you can see the percentage of search that was explored, as well as number of LLM calls that's needed to run all instances of these problems. Now, in this thought of search approach, we actually had a human involved to look at this code that was generated by LLM and verify it. In the follow-up work, which is on the bottom, we use automated testing. It's called AutoTOS. The number of LLM calls slightly increases, but you sort of have the human out of the loop to achieve the same sound and complete and reliable solution. The second promising approach is called LLM as a policy generator. So in planning, there's something called generating a policy, which is sort of like a strategy that will work in solving all instances of your problem. Just to give you an example, in blocks world, if you don't care about quality, you just want to find a plan, a simple strategy would be put all of the blocks first on the table, all the blocks on the table, and then, depending on the configuration of the goal, put them back and stack them. This strategy would work in all instances of blocks word. You don't need to have any search. You don't have to have heuristics. You don't have to have anything, right? It's a very simple strategy that will work in some planning problems that do not require search, not all. And if this approach works, basically you say, hey, LLM, give me a high-level strategy or a policy, and also write this policy in code, let's say Python code. And that will be all I need to solve all instances of a particular domain. So the papers that I highlight on the left here are addressing this problem. And what is interesting here is to how do you evaluate this policy? How do you know this policy is correct to begin with? Because it was generated by LLM still, and you have code. So you have to have some sort of a validation to make sure this policy is correct. And the last and very exciting line of work is LLM as PDDL generator. So what this means is that let's use LLM at what they're good at, which is given a natural language that would represent, planning description. Let's ask LLM to write a PDDL version of this problem. So PDDL, you recall, was the planning language that represents the planning problem in a compact way. Once you have the PDDL, all you need is any planner that we talked about in sort of the pre-LLM era. That's a sound and complete planner. By definition, they are sound and complete, and you use that planner to solve the problem that you have at hand. So this is a very powerful model elicitation tool that you can use. So all of these 3 approaches in sort of the modern LLM era are very promising. They do not call LLM at inference time. They're very efficient in the number of calls they make to the LLM, and they work toward a sound and complete, very reliable solution. All right, and with that, I conclude. If you want to know more about planning, there are a number of different tutorials that have been given. So the one I gave was very, very short. There is a much longer version of this tutorial that was given in NeurIPS 2025. That's the first link on the left. We also have many different other tutorials that we gave. If you're interested, to find out more about planning, that would be ICAP's conference. That's the main venue for all the planning literature. And furthermore, if you want to, sign up, there is some summer school that's happening in June in Dublin. So if you want, you can also sign up for the summer school to find out more. There's also a AI planning community Git on the bottom right that you can go to and get all the potential planners that that are available there, and download them and use them. All right, thank you so much. I'll take questions now. We do have 5 minutes, actually 4 minutes. Yes.
You mentioned there are 3 approaches for AI to generate the solutions, find the solutions. How do we choose which should use at different scenarios?
You mean the computational problems that I talked about, like whether?
No, the last slide. So
this one?
Yeah.
That's a very good question.
The pros and cons.
Yes.
How do we choose?
Yes. So that's a very good question. Depends on the problem and what you have access to. So if the problem statement is written in natural language, I would say the last one, which is LLM as PDDL generator, may be a good way to go, because then you get a PDDL representation of the problem, and you can run any planner that you're interested in, depending on the computational problem you're solving. What I find more promising, as I'm sort of investigating all 3 of these approaches, is that LLMs can do very well in writing code. So they're doing much better these days. For example, Claude is an example where I've seen good successes with writing code. So there's the second one, which is the LLM as a policy generator. I think has a little bit more promising. It's a more promising direction. It makes a little bit, and of course, all 3 of them makes assumptions. I didn't have time to go through the assumptions that they make, and you can find out more about them in the papers that I highlight here. So it makes a little bit less assumptions in terms of what the state representation will look like. It will also be in code, meaning that some of the glue code that's really needed. So in some of the applications of planning in agentic settings, you have to not only find a sequence of plans, but also figure out how they would run in execution. So for that, writing code is a good way to go, and LLM as policy generator I find a little bit more promising. But I think you can explore all 3. I don't think I have a bulletproof answer on which one is now the winner, but really depends on the situation as you sort of investigate a specific problem that you have at hand.
Thank you.
Any other question? Yes.
Sorry for very basic question, because I'm not very familiar with this field. So could you give me some insights on why do we introduce LLMs? Because if the problem can be formulated with, for example, PDDL, then using a conventional solver makes sense. So using conventional solvers, for example, PDDL solver, is very natural. So I think the problem itself might be changed. Then we needed to introduce LLM. So if you have any insights, please give me.
You're absolutely right. If you have the PDDL and that's all you need, then you can use any state-of-the-art planner and you're good to go. The problem these days is that nobody writes the PDDL, or getting the PDDL itself is difficult. So the third approach here is, okay, let's use an LLM to give us the PDDL. So that's sort of one way. And I come from, the industrial research where many people came to me and said, hey, nobody's going to write PDDL for you. So figure out how you can get a PDDL, learn the PDDL, whether some other learning tool or use of LLM. So that's one way to go. Another one would be, well, depends on what level of abstraction you're planning. So if you are using the planner, you're getting the plans, and then you have another execution piece that will execute this plan and see how it works, then all you need is to get the plan and then executing it separately. But if you're sort of having some sort of integration between planning and execution, then it may not be natural to just have a PDDL. You might want to go into a different path of, okay, let me get the successor state, let me get the goal, and maybe that's enough. Or maybe let me get the policy because I don't really have a search here. So it depends on what you want, but you're right. I mean, and we can see that a lot of literature has focused on the third one here, which is LLM as PDDL generator. Really, really popular now. A number of different papers came up very recently and is exploring as we speak. I don't know if that answers your question.
Yes, thank you so much. So basically, using LLM is very easy. So we can access this kind of conventional solvers with LLM simply.
It makes it possible, yes. Rather than somebody hard code the PDDL, you get the LLM to help you with that.
Thank you so much.
Sure, no worries. Okay, any other questions? No? Well, I'm going to be here throughout the day. If you have any other questions, feel free to come and talk to me during lunch or coffee break. All right, thank you so much.